Okay, just to say a few more words about this model. So it turns out, so what we're looking at again is distributed data compression problem, where we claimed that, other than the sort of obvious approach, given that we know how source coding works, that we can compress to entropy, that we can actually achieve the red region of rate pairs. What we'll see is that's also optimal, so this problem is solved. Now what's interesting is that for the example I just gave for this problem where you have microphones in two parts of the room, usually there you're sampling a waveform and you usually quantize it, right? So because you can't represent an infinite number of bits, right? So analog means infinite precision usually from the math representation, which doesn't make any sense practically because we can't do anything with infinite precision. And so usually we have to, for most practical problems, we have to accept some distortion here. So we might have, for example, some distortion constraint. We might have two distortion functions here, or perhaps we want to merge these two into one. Like it could be what's actually happening is we have a source here, let's say source signal, which then gets converted to signals like my voice, for example, and I'm interested in the voice signal. But let's just consider this model for the moment. So it turns out that once we have distortions here, then the problem is open. Probably, I mean, everyone has their favorite open problem in network information theory. This is, one of the ones I think it's the most basic, one of the most basic open problems in network information theory is to solve exactly this problem where we start permitting distortions here of the kind that you saw yesterday. Okay, there was quite a lot of activity on this about 10 years ago. I think the most important results were developed by Aaron Wagner's group at Cornell. At least I'm not an expert in the area, but just looking at it from the outside, that was my impression. Since then, there has been very little activity. Again, it's hard, or it seems hard. It seems hard. Maybe it's easy. Maybe you just need the right trick, right? I mean, usually once you solve these problems, you go, okay, that was kind of obvious. We should have known that, right? So maybe there's just some simple trick that's still missing. We don't really know because we just don't know, right? So, but that's an interesting problem. But okay, so here we'll stick to the simpler problem where we want distortion basically to be 0 because we want perfect reconstruction. We'll talk about another model in the next hour after lunch where we simplify it a little bit and permit distortion, and for that problem we can solve it too, and we'll every time we solve something we'll find new tools, right? And we'll learn that, oh, to actually solve the general problem we need something new. What is it that we need new, right? So let's talk about what we need new here. So we don't just want to compress, and certainly if I want to, we can even maybe study quickly one of these points. Usually it's nice to look at these corner points. Like if I'm operating, let's say here, at that point, you'll notice that the rate 2 is the entropy, so I'm basically just passing on the signal fully to the receiver, right? Now this rate here, though, has reduced, right, from here to here. That means I can't no longer perfectly, I can no longer perfectly represent this, right? I have to give something up, right? But somehow in the combination of the two we'll recover it. How will I be able to recover even though I can't represent it only from here? Well, I get information through the correlation, of course, right? If I see yn, I'm actually getting some influence from this side, and that's what I need to use. So how are we going to do that is going to be the interesting thing. Okay. So let's talk a little bit about a few things as a reminder. So to do the theory for this problem, I will need a few things just as a reminder. So we will look at the typical sets, and you saw one definition that yesterday was so in the Cover-Thomas textbook they like to use what I'd like to call entropy typical sequences. So you just look at sequences and compute a empirical entropy, and you see if it's close to what you want it to be. There's many different definitions of typicality. All of them are more or less equally good, so it's more based on your most favorite thing. There's some subtle things like this definition here, which I kind of like. It's also the one you'll find in the Elgamal, Kim Elgamal book. It compares the, if you look at this, so what does this represent? What we're doing here is we're taking a sequence, a pair of sequences, and suppose we just write this pair out, x1, x2, x3, up to xn, y1, y2, y3, yn, and then we look at this as a sequence of pairs, and we just count the number of times in the sequence of length n we see the pair a, b. So for instance, this position might have a here, b here. This one might not. This one might have it again, a, b. And then we'd have two instances divided by the length, right? So that's the empirical distribution in this pair of sequences of the letters a, b as a pair, right? So this is the empirical distribution. And if this empirical distribution is close to some chosen distribution, right? So if this here is less than some small number, and for some technical reasons, in the Covert-Thomas book you have something like this. You know, we make it just a little smaller. There's some technical reasons for it, which I'm not going to get into here. If this is true for all a comma b, then we say that this pair of sequences is epsilon typical with respect to this joint distribution. And you'll notice that I can choose those two separately, right? I can choose this distribution to be anything I want. As long as it satisfies this, it's epsilon typical. So that's the one I mainly work with in my little booklet. It's also the one that's used in the Elgamal Kim textbook. And just to review some properties of this sequence, you know there's various properties here. One is that the size of this set when n gets large is approximately 2 to the n hxy, right? For any pair that is typical, that is in this set, we have that the probability, and what I mean by this notation is just the product distribution. So this notation means that's defined to be I equals 1 to n pxy xi yi. Okay, that's what I mean by putting that little n up top here. Then this is approximately equal 2 to the minus n hxy. Right, you know that too. And then there's two interesting experiments to think about. Suppose we produce two sequences using the joint distribution of the source, like for the distributed source coding problem, we have exactly that source. Then, of course, the probability that the pair that comes out that it's typical is approximately 1, or that it's not typical. Well, let's write it like this. It's approximately 1, and so of course the probability that it's not typical is approximately 0. And in fact, the probability that it's not typical decreases exponentially fast with this block length, right? So we get an exponential decay. Now there's one other experiment that's important. Suppose we do the same. We generate two other sequences. Let me call it x tilde n and y tilde n. Okay, so it's a different experiment where we're taking the margin. Suppose we take the marginal of this px, py, we generate x tilde, y tilde. Now we can also ask the question, well, what's the probability that these two sequences are typical with respect to the joint distribution, pxy? And you see immediately, well, there's a mismatch here, right? I mean, this would be approximately 1 if this joint distribution corresponded to the experiment product distribution. But here there's a mismatch. So this turns out to be approximately 2 to the minus n, the mutual information between x and y. Okay, and that's not too hard to prove using these properties, but this is the reason actually. So this fact that if I'm producing two independent sequences, the probability that they happen to have some joint statistics, that the fact that the scaling operates like this turns out to be the reason why mutual information plays such an important role in communications. Okay, so one way of viewing this is that's the reason why things are the way they are, right? Exactly this result. Okay, and that's also what you used, I think, to prove your channel coding theorem, right? So you had two cases. One where this is the sequence that was actually sent over the channel to get y, in which case, they're jointly typical. And the probability that you make a mistake is if one of the other sequences was just chosen independently of y and happens to be typical by chance. And the probability of that happening is this. So how many other messages can we choose? Well, just by using the union bound, it's just 2 to the power of n ixy, so that gives you the rate, right? So that's how the proof works. And the same is true for the rate distortion problem. You use exactly this idea there too, right, to give your proof. Okay, so that's just some quick background. I don't think I need this other stuff. Oh, maybe one more thing. So this is a fully probabilistic version. We can redo this by doing a conditional version. Like, let's suppose we do this minor variation on this. Like, suppose we don't view this now as a random variable, but suppose we generated this sequence, and it's fixed. So suppose this sequence was generated out of here. Well, it's with high probability it's typical. So let's just suppose it's typical with respect to px, right, with high probability. And now let's ask a different question. Suppose I replace this by any typical pair and then just produce an independent y. Okay, so actually the new experiment just looks like this. Choose a typical x and produce just random y. What's the probability that those happen to be jointly typical? Well, it's again about 2 to the minus n mutual information. So it's just a conditional version of the original result. Okay, so we'll need that too, but they're basically the same result. I don't think that one should be so surprising. Okay, good. So that's background. So let's go into how we do our coding for our problem. Let's talk about it. So we have this distributed source coding problem, and what I want to first talk about is how we do a code construction. So we'll proceed in a very similar fashion to the rate distortion source coding problem. We'll generate a code book. Now there's different ways of approaching this proof, but so let me do it this way. I'll point out this approach will seem a little strange at first. I'll point out why, because, well, I'll explain why. Right. So what we're going to do is do the following. What I'm going to do is first generate a code book at encoder 1. This code book, what's going to be different about this than usual is that usually we generate a code book, for instance, for the channel coding problem, you generate using px. You generate, say, 2 to the nr sequences at random by choosing every letter of every sequence independently using px, right? That was the classic random code construction. So we're going to do exactly the same thing here, except for one small difference. I want to build in 2 indices rather than 1. That's the only thing I'm going to do new. So I'm going to have 2 indices, 1, 1, and I'm going to run the indices, the second index, up to some new number, r primed. And then it comes the new 2, 1, the next grouping. So I'm going to call this here a bin, or a subcode, bin 1. Similarly here, there's going to be some bin 2. And similarly here, there's going to be some bin, and the number of bins I'm going to have corresponds to the number of bits I'm going to send out of the first encoder. So this one will have two parameters, to the nr and to the nr primed. Okay? So you'll notice the code book, the whole code book has gotten bigger than before. And what I'm going to communicate across, after I compress at node at the first encoders, I'll just send the first index. Right? So the code construction is this big code book. What I will actually send is only the first index. So choose 2 to the n r plus r primed xn w1. So I'll have two indices, w1, which I transmit, v1, which I'll throw away. Right? I'm going to throw that one out. By choosing every letter independently via px. Okay, that's going to be the code book I build at terminal 1, and I'll do the same thing at terminal 2. Similarly, or not terminal, encoder 2, at encoder 2. So this is encoder 1. And this is at encoder 2. We have yn sequences w2, v2, where this runs from 1 to 2 to the nr2, and this runs from 1 to 2 to the nr2 primed. Okay, so same idea. Right, is that clear? Just generate the code books in the same way as before. How do we do now our encoding? Well, that's going to be quite straightforward. So the encoder 1 is given xn. Try to find that x in the codebook. And if it's in the codebook, we're happy, and we send the first index. So find a pair w1, v1 such that xn w1, v1 is equal to xn, and send w1. And if you're not successful, then you just send a default index. Okay, but we want to have conditions where we'll be successful here with high probability. Now this may seem a little weird. Let me explain why. Right? I mean, in the end, we know that whatever comes out of the source is going to be typical. So why not with high probability? So why not just choose the set of typical sequences? Why am I generating a random code book? You can do that. So that's, if you look at the Cover-Thomas textbook, that's the approach they take. They use just a set of typical sequences. The reason I'm generating these things independently in this funny, why I'm generating it independently, is just to get more independence. Once I choose the typical sequence, there's already a lot of dependence inside the code book because I've already restricted myself. It's no longer IID, right? Now I'm looking only at typical sequences. Of course, those are the important ones, but you get dependence that you can't get away later. You have to do, the proof goes a little bit differently. So here I'm just generating the code book independently. The other reason I do this is because later we will be looking at similar kinds of constructions where what I'm generating doesn't correspond to, the sequences coming out of the source, but something else. So there's a reason I like to do it this way. I want to extend the idea later. Okay, but is it clear? Yeah.
So we separated into two different mappings.
Yeah.
Again, that R1 why did we do that?
Why do we do that? You will see. You'll see. Well, the main reason is actually, and maybe I can say it quickly, is to be able to find this, for this to be successful, the size of the whole object has to be the entropy, 2 to the power of nhx. But what we want to send is smaller, right? So the step of finding, being successful in encoding, requires a larger code book than the index that we're actually sending. So we've artificially enlarged the code book beyond just having these indices. But this will be useful later too, and you'll see this idea appearing for broadcast channels and for many other problems too. This idea of enlarging the codebook size to accomplish something, right? So that's the reason we do that. Yeah. No, we're not going to safeguard against that. Of course, practically yes, but for the proof, no, it's just IID coding. But the same thing happens for channel coding, right? You're generating just a code book. You could have the same code word. The probability of that happening is very small, though. And it turns out to be much smaller than the error probability that you're interested in. Oh, yeah, find any. Of course, if we find, if the same one somewhere else, we could send that one too, right? We're fine with that, right? Yeah. And yeah, so if there's more than one, choose one. That's right. Yeah, that's okay. Encoder 2, similar, right? Same idea. So what we'll need is conditions on the size so that those steps are successful. And now, before we do that, let's go to the, well, actually maybe we can even do that right away. Well, let me go to the, well, maybe. Okay, well, what's the probability that we will be successful? So let's look at the encoder 1 success. What's the error probability going to be? So the probability that there is no W1, B1 such that Xn, let me make it capital because it's a random variable, W1, B1 is equal to Xn. What's that probability? Well, we can write that as an intersection of events, right? That's the probability of the intersection over all W1, V1. That's the event that Xn W1, V1 is not equal to Xn, right? Moreover, all these events are statistically independent, right? Because, well, I have to be careful. If I condition on Xn, it's going to be conditionally independent. So let me do this. I can write that like this. It's going to be the sum over all Xn, Pxn Xn. Probability, so just by the law of total probability, where actually this is just Bayes' rule. I guess I should put it that way. It's W1, V1, Xn, W1, V1, and now I have a fixed Xn, given Xn equals Xn, right? So I have this, it's just Bayes' rule, right? Or actually it's law of total probability. I should say it that way. Now if you look at these, this event, not equal to Xn, right? This event, I claim that this event and this event are statistically independent. Do you see that? This here is the source, and notice that I generated the code book completely independently of what came out of the source, right? So the event that the source variable is Xn and that the code word is Xn are independent. So I can drop this. Moreover, all of these are independent too in this intersection, so it just becomes a product, right? So this whole thing is nothing other than the summation of Xn Px. Sorry, I tried to stop that screeching. This all, and not only are they independent, they're all the same. Not only that, we can write out exactly what it is. It's 1 minus Pxn of Xn raised to the power of 2 to the, how many values we have here? 2 to the n r1 primed. I'm probably writing completely unlegibly, so let me pull that here to the top. So this here we can write stuff with equality all over the place. So this just becomes the summation of Xn, Pxn of Xn, 1 minus Pxn of Xn, all raised to the 2 to the power of the number of things we have, which is the size of the code book, R1 plus R1 prime. right? That's all it is. Okay, now we'll use the same trick that was used yesterday, namely 1 minus x is less than or equal to e to the minus x, and if we raise that to the power of y, we can just raise that to the power of y, right? And so this whole thing is less than or equal to exp minus x times y, which is going to be this. So I'll have to make a small adjustment in just a moment, but let's not worry about that right now. And now I'll worry about it now. Okay, here we go. So now, when I talked about this error probably here, I'm still summing over all sequences. But what I can do is I can now split these sequences into those that are typical and not typical. So in fact, I can write this thing here as the probability that I'm not typical, you know. So let's just call that delta, which goes to 0 as n goes to 0 as n goes to infinity exponentially fast, plus this set, which is the typical set. Right? I can just do that because this number is always less than 1. So I can write that error probably this way. And now here, since this is typical, I have, what is this? We just wrote that before. That's approximately 2 to the minus n, the entropy, right? So in order to make this probability small, I have to make R1 plus R1 prime bigger than the entropy, which makes sense, right? Because after all, to get all typical sequences here, I need to have a code book at least that size, 2 to the n h of x. But what this tells me is that in terms of scaling, exponential scaling, that's all I need. So I could generate this code book maybe a little bit bigger than the entropy, but only an epsilon bigger than the entropy because the exponential scaling takes care of making the error probability small. Okay, so that's the first bound we get. So for this step to be successful, I need 2 bounds, namely, so for encoder 1 success requires R1 plus R1 primed bigger than h of x. And similarly for encoder 2, we have the same kind of result. And this should be intuitive, I hope, right? So that, in other words, we don't really pay a price for doing random coding as opposed to choosing, you know, just all the typical sequences. In practice, you wouldn't want to do this, what I'm just doing here. But of course, random coding never makes sense in practice, as far as I can tell. It's a theoretical tool. It's not a practical tool. Okay, but anyway, this step will be, these steps will be fine as long as I have these rate bounds are satisfied. Now, okay, so that's one thing. The next thing we have to worry about, of course, which is going to be a little bit more important, is what happens at the decoder, right? The decoder, so let's keep those 2 things in mind. Right, so the decoder sees this W1 and W2, and now what it must do is try to find the pairs it is missing, right? V1 such that, and what it's going to look for, what extra knowledge does it have about the model? Namely, it knows that if this was successful, if these 2 steps were successful, then those 2 sequences corresponding that were found inside the 2 code should be jointly typical, right? So that's what it will try to find, such that xn w1, which it knows, v1 tilde, and yn, which it knows this index for, is in the jointly typical set, which it knows it should be too, because with high probability that must have happened of the pair that came out of the source. Okay, so that's the decoder operation. If it's successful, so if it finds such a pair, you know, that's then the estimates, x and yn. If it doesn't find such a pair, put out a default sequence. If it finds more than one, well, just pick one and put that one out. But effectively, we'll only declare a non-error if we find one, and of course, if it's the right answer, right? So now what we have to do is try to find conditions on these sizes of code books as well as subcode books so that this whole thing works. Now, in fact, since we know W1, we know, like suppose we see W1 was 2, or let's say 1, then we know we have to look into this subcode book. And if W2, let's say, was the last index, then we know we'd have to look in the second subcode book. So we're only searching in those subcode books that concerning the information that we got. Okay, and what we have to hope is that in that code book, well, what do we have to hope for? Well, there has to be at least one jointly typical pair in there because, the original sequence is typical, so that we would only choose that pair if there was a typical sequence inside. What we have to hope is there isn't another one inside. Because if there's another one inside, our error probability will be at least a half. If there's 2 more inside, it's going to be at least 2/3 because we don't know which one to choose. Right? So what we have to show is we can't choose these subcode sizes too big, right? If we choose them too big, for sure we're going to get some more than one pair that's jointly typical. So what we should be looking for is a bound on R1 primed and R2 primed as a pair. What combinations of R1 prime and R2 prime can we choose to ensure that we see not more than that exactly one sequence that was jointly typical? For example, if this was size 1 and the other one was size 1, we're fine. But then, of course, R1 has to be the entropy and R2 has to be the entropy. So we're back at that trivial point again, right? Which will work, but it's not we're hoping to do better, right? So we do have to, and that's why we enlarge these code books, right? It's to do compression. Compression beyond the classic compression. We're going beyond the classic compression, compressing more, right? We're asking how much more can we compress. Is that clear? Trying to accomplish? Okay, so let's look at what can go wrong at the receiver is exactly what I just described. So let's give this a name. So the error event that we're considering, now in my notes I have like E3, but let me call it E1 because I've already taken care of these error events. So that's the union of events that there is a pair V1 tilde, V2 tilde, different from the one that was actually sent. And let me call that V1, V2. I write it big just to emphasize that in a moment I'd like to consider it to be a random variable. So this notation is a little bit funny because this is actually a random set now. But you can think of it as a fixed set, but when I write a probability around it, then everything will be fine again, right? Because it's a probability of something happening. Anyway, namely that, so it's the union of the following events, namely that there is a jointly typical pair where this is the known W1 and this is possibly an incorrect index. Again, possibly an incorrect index, but the pair definitely is incorrect, is typical. Okay, so that's the error event that I would like to bound in combination with the event that X and Y are themselves typical to begin with. Okay, so let's look at that. Probability, that's the one we have to worry about still to get bounds on the rates. Okay, so let me do the following. So let the basic error event just be that you're typical, right? So I just want to say that this here is that the original source sequences. So this is the sequences coming out of the source is not typical. And we know that error probability is small, right? And so what I want to bound now is the following. The probability of E1 and E0C. So this is just the event that the pair is typical. The pair is typical. But this event happens. Okay? And now I can write that using, again, the law of total probability. Let me start with writing this as the summation over all x and y and that are typical. Probability of those two sequences. And then I have a conditional event now, namely the probability of E1 given xn equals xn, yn equals yn. Right? And now I'd like to worry about this. Okay, and I know these two sequences of yn. I know this and this are typical, jointly typical, right? Because that's why I introduced this E0C, is I just want to make sure what I'm conditioning on is typical sequences. Now if I look at that, I'm getting a union here, so if I plug this thing in here, I get this union. And now I can use the union bound to upper bound this. So union bound. So nothing particularly exciting. So I'm going to get all v1 tilde v2 tilde not equal to v1 v2 of the probability okay, so I have to write out the whole thing again, right? So it's going to be xn w1 v1 tilde suppose, you know, if formally again I should, I'm viewing these as random variables. What I should do is then view them, write this out as, you know, the probability of what v1, v2 were and then condition on that. But I'm just going to use the simplified notation, even though I should worry about it a little bit more carefully. But anyway, this here is this. This is already one place where I'm arguing more, a little bit more intuitively. I would need to do a little bit more formal steps to do this. But anyway, suppose we effectively have this via the union bound. And what's going to happen, so here we're conditioning, again, we keep the conditioning. What we effectively now have to do is I'd like to bound each of these individual objects. Now it turns out there's three cases I have to worry about. Namely, when is a pair not equal to another pair? Well, when either of them isn't the same or when both are not the same. And those are the three cases I have to worry about separately, because if v1 tilde happened to be v1, then this is a typical sequence, namely xn. It's exactly that sequence that was put out by the source, right? So this will be little xn, and then there's going to be something happening. But suppose I do that. If I look at these three cases, what's going to happen? Suppose v1 tilde is v1, but v tilde tilde is not v2. Well, then this will just be little xn, and what will this be? Well, it'll be a code word that was chosen independently of what I'm conditioning on. And so I have the case that we saw before where this was little xn, this was an independent yn. What's the probability that this is jointly typical? It's 2 to the minus n, the mutual information between x and y. Okay, let's do the other case. This is v2, this one is not. Well, that's just the same. And what if both are different? Well, I get the same thing. And so how many terms do I have in here? And all with the same bounds. This whole thing is going to be the number of terms I have, which is going to be less than 2 to the n r1 prime plus r2 prime. And for all of those events, I'm going to get, now I should write here approximate because there's little twiddle factors up here, right? Plus epsilon, minus epsilon. But effectively, I'm going to get this. So the bound I get is going to be r1 prime plus r2 prime has to be less than the mutual information. And that's going to be my bound on how big these sub-bins are. Okay, so that I get out of all of this what I'm going to get. And this is a number that will appear for us again in the broadcast channel when we look at the dual of this problem. So we'll look at the same problem again for broadcast channel, just the dual version, but we'll get a similar bound. So decoder success. What we need there is the following bound, r1 prime plus r2 prime I xy. So what's interesting about this is the sum has to be bigger. We have no individual constraints other than, of course, you know, if this is 0, both have to be positive, non-negative. R1 prime has to be non-negative. So we do have to have this and this. but the only constraint we need is the sum. So it's really the area of that box that plays the important role. We can stretch it or squeeze it, but as long as the area is this big, right? What do I mean by that box? I mean the box where I have here, this is W1, this is W2. These are all the W1 sequences, xn W1 of 1, xn W1 of 2 to the nr, 1 primed, right? And on this axis, I have yn W2, 1, yn W2, 2 to the nr, 2 primed, right? As long as the area in here satisfies this, right, when I'm stretching it or squeezing it, moving around, I will find, less than. As long as that size isn't too big, I will not find another typical pair by chance, right? That's the point. Okay? For example, I could choose both to be 0. Then the area is 1. That certainly will satisfy this, so, as long as they're not, unless they're independent. But then otherwise, if there's any dependence, then I'm satisfied. But the problem then is I get, the bad coding. But now I can improve my rates by compressing more, right? Sending less information to the receiver. So if we combine these two bounds together, now what we should formally do is apply Fourier-Motzkin elimination to get rid of the r primes, to get bounds on R1, R2. It's pretty easy to do in this case. Here we need, anyway, so as long as these three inequalities are satisfied, error at encoder 1, error at encoder 2, error at the decoder, then we can achieve these rates. And now we just put the rate constraints together. So if we look at the first one, what we have to have is R1 has to be bigger than h of x minus some reduction. For example, if I choose R2 prime to be 0, I could reduce by the mutual information. And what is this? This is h of x minus h of x given y. Oh, get exactly that quantity that we were looking for before. We'll also get R2 has to be bigger than h of y minus ixy. And then we'll also need a bound on the sum rate, it turns out. Because you'll see if you sum these two together, we'll get h of x plus h of y. And this turns out to be the same as the Fourier-Motzkin elimination. I haven't done it here. And what is mutual information? Well, it's h of x plus h of y minus the joint entropy, right? And that's the result we wanted, right? So that's how the proof works here, and also how the coding works. So the coding works. How can we? In fact, we can even build something like this practically for some problems. But before we do, let me do one example. So, are there any questions about what I just did first? Okay, again, it's only an outline of the proof. I was a little bit cavalier in how I wrote that union bound because I wrote it with a random variable in the indices at the bottom. So you have to think about what that means. The easiest way to do that is then just use the law of total probability to write v1 is little v1, v2 is little v2, and then you have to condition on that as well. And then you do it. But I did it a little bit fast, so you have to worry about that. So anyway, let's do an example. Let's suppose x is Bernoulli 1/2. Let's suppose y is x or z, so that everything's binary, where z is Bernoulli p. Right, so the correlation is there. As long as p is not a half, then we get a correlation between x and y. We can all we have to do is compute these numbers. So let's compute those. H of x, h of y is of course 1. Bit h of x. Let's do y given x. Well, it turns out they're the same. Y given x is easy, right? So if we're given x, then here we get x or y. And that's just entropy of z, right? So this is just the binary entropy function of p. I think in my script, do I use h2 or do I use hd? I think yesterday you used just h of p, right? So that's another way of doing it. It's a little bit, then I use h2 of p. Matthew Bloch tells me I shouldn't use 2 because in secrecy that's some other metric, but I don't care, so I use it 2 anyway. Some people like to write binary. Some people like h, but then it's again overloaded, right? So we're running out of letters, unfortunately. So let me just write it like that here. And then the joint entropy is easy, it's just the sum of the two, right? So if we plot this, and let's do an example where we, p is 11%. 11% is a nice number because then the binary entropy function of that is about a half. Or approximately a half, whatever. Okay, so what we're getting is this number here is 3/2, and these numbers here are 1/2. So if we plot this region, we will get a region that looks like follows. So I need 1, I need a half, I need 3/2. Half, 1, 3/2. Here's my joint entropy bound, and here at the half is where the conditional entropy is lying. So that's this and this. So this is my region. And if I was to compress separately, I would only get this. In fact, I wouldn't be able to compress at all because both bit streams are uniformly distributed, right? So if I use the separate compression scheme, I could only operate at 1, without any complexity whatsoever, of course, no coding. But if I did decide to use coding, I could get points here. So let's talk about one of these quickly, because this example is particularly interesting. This particular source. Let's talk about one of the corner points that we talked about before. So how could I build a code that does this, that operates right at that point? Well, the Y sequence, I'm not compressing at all, right? Send it off to the receiver, right? Now, the other sequence I do have to compress down to half a bit. How can I do that with bits? How can I compress? What's the nicest class of codes? Just a very general class of codes. Don't tell me Ldpc or anything like that, or polar. Don't tell me polar, because it's a subcase of the codes I want. Linear codes, right? Linear codes. Okay, polar would work too. Although only if they're really, really long. Anyway, polar codes would work too. Linear codes work. How do I do it? Well, what can encoder 1 do? I take the sequence of xn and I pass it through a parity check matrix. Right? So what I'll do is I'll make my message vector or sequence, in this case it will be n by 2, maybe a little bigger, will be a parity check matrix times xn, right? Where this parity check matrix is n by 2, n times n by 2, right? And what is parity check matrix? The same thing as hashing. We're effectively just hashing the bit string down to a shorter length, right? So we're just doing a hashing. Which parity check matrix must I choose? Well, I have to choose one, it turns out, from a good error-correcting code, because the Y which I see, well, you can view this as like going over a noisy channel. It turns out that if you choose this parity check matrix as a parity check matrix from a good error control code, then you can use the same decoding algorithms for that error control code to recover xn from the yn sequence that we see. It's like observing noisy channel output and the subset of the compressed bits. We can use that, and we can, in fact, you can choose any good code. You could choose an Ldpc code. We could draw its diagram. What will the Ldpc code graph look like here? We can quickly draw that. So if we had suppose we had a graph of a parity check code, right? So here we have the x's. xn, let me draw them above. Here are the nodes, these are bits. What we observe at the receiver are the noisy versions of this, y2. So xn is hidden to us. But then what we do see is if we have this big parity check matrix, we get a certain number of nodes coming out, right? We're thinking of an Ldpc code. And this is this W1, W2, W, let's say n by 2. Right? So we see this. Now in classic error control coding, all these numbers are 0, right? They're parity checks that evaluate to 0, usually. Here they're not evaluating to 0, right? They're evaluating to whatever the hash gives us, but we know what it is, right? And using this knowledge and the channel noise, we exactly have a classic decoding problem, you know, where we're just passing messages back and forth. So in fact, designing good codes for the distributed source coding problem, compression codes, is the same as designing good error control codes for a channel going from X to Y. Exactly the same problem. You see it in the diagram here. So it's one-to-one the same thing. And so back in the 1990s, when turbo codes came along in 1993, those people working on source coding, you know, you could see this. In fact, how Slepian and Wolf first approached the problem was exactly like this. They approached the problem from a linear coding perspective and showed that they could get these corner points using exactly this picture. And then they showed, oh, I can get that corner point too, and I can get everything in between by time sharing. Okay, that's how they, if you look at their paper from the early 70s, I think 71 or 72 or 73, that's how they present the solution to this problem, is like this. Okay, and in the 90s, people then actually built. They took turbo codes. That was the first papers were from, oh, what's his name? The Spanish person. It's not popping into my head right now, but he took turbo codes, put in here a parity check matrix for the turbo code, did the turbo code decoding, and showed you could operate really close to this point in here too. Okay, and if you like polar codes, you would take a polar code, and then you can also show as the polar code length grows, you'll get as close as you want to that point. Okay, and the same idea for other source-destination pairs. All right? So the coding is like channel coding for this problem. Any questions about that? Okay, that's kind of interesting. You know, we have a new tool, this having 2 indices rather than 1, which corresponds to compressing. We have an algorithm how to do that. In fact, any kind of binary representation we get of a source, suppose we didn't have a binary source but a higher alphabet one, well, you could compress it down to a binary representation, and then in the second phase do hashing, because the binary representation is like a bit sequence. So what you can actually do for more general sources is first convert it to a sequence of bits and then do hashing after that. That works too. Very practical approach, because it sort of separates the representation from the further compression, because there's 2 compression steps here. Taking the original source sequence, doing something like a Huffman code to get a binary representation, and then using the hashing to get down to a shorter bit sequence, and then decoding on that structure. Of course, the problem there will be the Huffman code. It has a weird representation, so you probably don't want to use a Huffman code, maybe something else that is nicer to work with, like a polar code. I always look at Civi because his supervisor is in love with polar code, as are many other people. So. Okay, so there's one more thing, if there are no questions here, there's one more thing I do want to do, and that's the Converse Theorem, to show that we actually can't do better than these bounds. That's not too hard. I just have to do these things the right way. So let's just do the converse step. And what I'd like to do is just do it for the first bound. So we have these 3. I'll do it just for the first because the steps for the others are the same thing. So the first thing we see is, well, what can we say about the bits that are put out by encoder 1? Well, that's definitely got to be bigger than the entropy of the message, right? Because the number of bits we need to represent the message we send down the first transmitter is at least, this NR1, right? Just by the classic compression result. And then we start working from there. So this thing here is greater than or equal to, let's just add conditioning. So this is a trick step already. So we add conditioning on y1n, and we'll also subtract off both. And just like yesterday, we should ask now, when is this bound tight? But it's only going to be tight if the message is going to be independent of the other sequence. So whatever we're sending optimally to compress down better be statistically independent of the message. That's an interesting insight, right? Because usually if this here was representing xn, we wouldn't necessarily think it would be independent of yn, right? Because this w1 sort of represents xn, but it does represent less than xn, right? Because we're compressing further. And in fact, what we'll need to actually have happen is that the messages we send down both links should become statistically independent. That's necessary, which is also intuitively makes sense, right? Because if there was any redundancy in those two, we could remove them perhaps by compressing more, right? And that turns out to be true from this step. We'll see in a moment because we'll get the tightness here. Okay, this one says we better want this to be 0, but that says that given both, we can determine W1. That makes sense because this is actually a function of that, right? So this is 0. In fact, there's nothing lost here. The reason I wrote that is so that I can write a mutual information expression, xn W1 yn. And so usually these tricks are just to turn the thing around. Xn given Wyn. Okay, now we're almost there. Like, this is what I want. Since this is an IID sequence, this is nothing other than h of x given y. However, if this is positive, it might permit me to compress more, right? So I have to make sure this number gets small, close to 0. How can I do that? Well, what we'll do is we can make this thing here is less than or equal to, greater than or equal to, no, I want this to be less than or equal to something, right? So let's see here. I have to make sure I can add a few more things here, so let me add that. What can I add to this? Since I know yn, I can get w2, right? w2 is a function of yn, so I can stuff that in here. Once I know both of these, I can get the estimates, right? Right, because the estimates are functions of the two indices arriving at the receiver. So I can stuff all these in here. So this here is equal to this minus all of these. Let me write that out formally. W2 right? And now this thing here is less than if I drop everything except for the estimates, right? So this thing here is less than or equal to right? And it's also less than equal if I add that at the front too. And this thing here you should recognize from Fano's inequality. We have from Fano's inequality, this thing here is less than, so the error probability is the probability that this is not equal to that. So this thing here is less than the binary entropy function of the error probability. This is just Fano plus PE, the logarithm of the set sizes, so log of x to the m. That's the set size of random variable x, set size of random variable y. Anyway, I know I'm doing it a little bit fast, so let me just continue this up here. So this whole thing is bigger than or equal to nh of xy plus n times the binary entropy function of the error probability divided by n. And here I can take the logarithm down plus PE log of the set sizes. Right? And if I want P to go to 0, what happens? This goes to 0, and this also goes to 0, right? So this whole thing, it shows that the rate for reliable communications, which is what I want, we have R1 bigger than h of x given y is necessary, right? Okay, is that clear? I mean, I think the last steps were perhaps a little fast, but it's mainly Fanos and writing out stuff which are really straightforward, then making sure you apply Fanos and equality. Then you can show if you want to make the error probability small, you've got to have this happen. Okay, and the other converse bounds work exactly in the same way. It's the same steps copied. Okay, so that shows this is the best we can do. But we also gained some insight, again, to make that tight. If I draw out the problem, again, xn, yn, this is encoder 1, encoder 2. We saw how to do compression, and what's most important, or most important, not necessarily most important, but what's important to get close to, what we've seen is to get close to these boundary points, we have to make sure these two are statistically independent. That's what we want. So we want to make sure these two still represent the source given the knowledge that we have about their correlation, and at the same time we want to make them statistically independent. That's how we get to these boundary points, these ones here. These are the important points, right? Because everything else is wasting bits. So these, we want to operate on that purple curve, and the only way we can operate close to that purple curve is if we make both bit streams statistically independent, or close to statistically independent. It's sort of an interesting insight. And again, we can do the encoding in a separation-based fashion, I'm claiming. Namely, we can separate the representation step into h of x, and here we have a representation step as h of y. And then as a second step, we do a hashing, just a pure parity check code hashing, so a linear hashing down to h of x given y. And here we again also do a hash down to h of xy. Well, I have to be careful. I have to be careful how much I'm doing hashing. Let me write it differently. R1 primed hashing and R2 primed hashing, right? So that we get the overall rate is the difference of the two. Okay, and that's how you would design and practice also these encoders. First represent by bit string, after that hash down using a linear code. Linear codes are nice because, of course, they have a lot of structure. Might be other ways, but the nice thing is this sort of a two-step procedure that we're doing. Okay, and then the decoder has the problem of then recovering this step and then recovering that step, right? Yeah. Okay, yeah, it's interesting to try it out. It works, right? So you can run it on a simulation, especially if it was binary source. If it's like other more complicated sources, of course, what happens if we have a Gaussian source? What happens if we have a Gaussian source? Does this whole thing work? Well, what's the entropy of a Gaussian source? This is not the differential entropy. This is the full entropy. Well, it's infinite, right? Because a Gaussian source has infinite precision. Right? So if this was Gaussian, then we're basically looking at a problem that has no real engineering relevance here, in the sense that I'm trying to perfectly reconstruct an infinite precision object at the receiver, and that doesn't make a lot of sense. So looking at this problem, we're really focusing on discrete random variables to begin with. If we start introducing distortion, then it starts getting interesting, and that's what we'll do after lunch. So we'll look at a special case of this problem where we do have Gaussian, but where we, of course, are introducing distortion, which is the only thing that makes practical sense for Gaussian random variables. Okay, questions? Again, sorry, I skipped a few details in the proof. If I did that, it would just take too long. But I hope you get the most important thing is to get the general idea. Good, so let's stop for lunch, and after lunch, we'll talk about this variation once we introduce distortion for this problem.